You have fallen into Event Horizon with John Michael Godier. For today's discussion of the possibility of extraterrestrial life, John is joined by Sara Imari Walker. Sara Imari Walker is an astrobiologist and theoretical physicist interested in the origin of life and discovering alien life on other worlds. She is the Deputy Director of the Beyond Center for Fundamental Concepts in Science and a professor in the School of Earth and Space Exploration at Arizona State University. She is the recipient of the Stanley L. Miller Early Career Award for her research on the origin of life, and her research team at ASU is internationally recognized as being among the leading labs aiming to build a fundamental theory of understanding what life is.
Sara Imari Walker, welcome to the program.
Thanks. It's great to be here.
Now, what is assembly theory? Give us a rundown of exactly where we're starting.
Yeah, assembly theory grew out of a desire to be able to solve the origin of life and really understand what life is at a fundamental level. And the key conjecture of assembly theory is that life is the only mechanism the universe has for generating complexity. So complex objects don't happen spontaneously, they only happen through evolution and selection. And assembly theory is a way that we can formalize both theoretically and in a way that we can actually make predictions in the lab and test it by measuring sort of complexity in molecules. And so it becomes a way for us to actually talk about evolution as a physical property of materials that get generated as living systems emerge and become more complex.
Now, chemically speaking, how does this begin? So the Big Bang happens and we see hydrogen, and eventually at some point you can have molecules and things like that. But then you get to DNA, which happened here on Earth. Do you think that's common? In other words, has your research led you to any direction that says this happens a lot or it doesn't happen very often?
I wish I knew the answer to that question. I think that's sort of one of the driving questions in my whole career and many other people's. I don't think that we're at a point where we can say whether life is common or not because we don't understand the exact mechanism. What we're trying to do with assembly theory is pin down the mechanism and be able to say quantitatively how often the origin of life can happen in different planetary environments. But we're not quite at the state where we could actually make a definitive statement about that. But I think it's interesting in your example, you talk about DNA, and DNA is obviously a very complex molecule and evolved here on Earth. So another sort of interesting question in that space is not just whether life emerges on other planets, but whether it would discover the same kinds of molecules in different planetary environments. And right now I'm of the mind, although, sometimes it changes depending on how the science is developing. But right now I don't think that evolution played out in a sort of a geochemistry on another planet would necessarily discover the same kinds of biochemistry that evolved here on Earth. And part of the reason for that is just that chemical space is so huge. And what we see with assembly theory is a huge amount of contingency that very small changes in sort of simple molecules can really change a lot of the structure of the more complex molecules that evolve from them. And so it might be the case that there is life elsewhere in the universe, but it has radically different chemistry than anything we've even been able to imagine here on Earth as the possibilities for alien life.
So what might that look like? In other words, all right, so say it doesn't use water as a solvent, say it uses ammonia. Mm-hmm. Does that change the chemistry dramatically into something that if we tried to test for it, we might not even detect it as life? But if we looked at it, we were like, well, that's acting like it's alive. Does the basics, the idea of water versus ammonia versus boranes or whatever play into this?
I have not focused so much on like the real basic questions about the solvent for life, although I think that's a really critical and interesting question. But the more important, sort of more general question, I think, in my mind, is whether you have a system that's capable of evolution and complexification. And what I think about more is just that the space is so huge that it's really hard to make predictions about those alternative possibilities. And this is one of the reasons that I really think that an experimental paradigm for the origin of life that really is embracing the fact that all of these kind of different planetary environments really could give rise to different kinds of chemistry is really critical to making progress. So it's not so much about alternatives to carbon-based chemistry, but even just in the space of carbon-based chemistry, do we really have any confidence that the aliens wouldn't really be just radically different? So I don't even think you actually have to go to alternative solvents or talking about silicon-based chemistry or all of these very exotic scenarios. I think even just within the space of carbon-based life, we really don't know much about the possibilities. And a simple example is just to think about amino acids. There's 20 amino acids that are coded in the genetic code roughly. It varies from organism to organism, but those make up proteins and are a core to the biochemical machinery of life as we know it. But we know of hundreds of amino acids that have been actually studied in the laboratory, and they're found, some of them are found in meteoritic samples, so we know that they're prebiotically available. And there's potentially thousands of amino acids if you just do structure elucidation, like in a cheminformatics sense. So even just like very simple building blocks that life uses, if you try to look at the possibility space for those, it's quite huge. And that's not even considering the chemistry outside of life as we know it. We're just starting from what we know and trying to expand outward. So I think we radically underappreciate just how exotic chemistry could be on different planets.
That makes a lot of sense, though, because, chemistry is the ultimate and complicated.
Yeah.
It's worse than physics.
Yeah, that's one of the reasons I'm a physicist and not a chemist.
Yeah, exactly. It's easier. Although people go into chemistry and they think, no, this will be easier, but no, it's not. And there's just so much. I mean, just look at, organic chemistry. The complexity of it is mind-boggling. And it just, the possibilities. Now, RNA versus DNA. So that alone sort of illustrates what you're talking about, that, you can have essentially two different systems, even within the biology of planet Earth, with a very simplest life. So what do you look for in an astrobiological sense? So if you're looking out in the universe, say you're on Mars and you're trying to detect some type of life as you don't recognize it, and your new book, Life as No One Knows It, which comes out, I believe, August 6th, right, it goes somewhat into this. How do you find it? I mean, if we don't know what to look for with life, how do we find it?
Yeah, so the traditional approach has been to look for things that we know are present in life on Earth. So there are efforts, for example, to try to look for other DNA-based organisms, for example, on Mars, or to look for amino acids on Saturn's moons. Like there's a lot of effort to try to find things that life on Earth uses in other planetary contexts as a potential window into alien life. The challenge there is just goes back to what we were just talking about. If you assume that all life in the universe is the same as life on Earth, that's great, but we actually don't know if that's a really good working hypothesis or not. It's one hypothesis. But the chemical space is so large, and the possibilities for alien life could be quite broad. And so one of the things that I have worked on a lot in my career is trying to think much more broadly than that. So if you think about life not as the chemistry that it's made of on Earth, but actually think about what is universal to every living thing in the universe. And are there any regularities that would really just describe life very broadly? And could we actually look for those kind of features or patterns and recognize those and be able to detect alien life independent of the chemistry that it uses? And that's really the approach that we take with assembly theory. What we're trying to do is not focus on what evolves specifically on Earth, but actually build a more general framework for recognizing when a molecule is necessarily the product of evolution and being able to measure that feature as a feature of the molecule itself. So if we go to like an environment like Enceladus or Titan, which is even more exotic, Titan's this crazy moon of Saturn that has liquid methane lakes and, all kinds of hydrocarbons on its surface. And Dragonfly is going to be going there as soon as the NASA mission. It won't very likely if there's life on Titan, which is a big if, but there could be, and it would be incredibly exciting if there was. It's not going to be like life on Earth. And so what we've been trying to do is actually develop these methods for being able to just detect complexity as a feature of living things and be able to just target that directly, which should happen in any kind of chemistry. And so it should be what the community calls an agnostic biosignature, so one that's not really focused on the chemistry of life as we know it, but more general than that. And assembly theory, I think, is particularly powerful in this regard because it's the only agnostic biosignature that actually has really a strong theoretical foundation. And this is what I've spent most of my career working on, is really just trying to understand the fundamental nature of life and trying to think about how do we actually quantify the origin of life and really understand the origin of life transition. And this theory is really promising on that front and also on the life detection front for the same reason that it's really general and it's very deep and broad in what it could potentially explain if it's proven to be right in the long run. And so the idea of life detection there is we have this property called assembly. Assembly is basically looking at how complex molecules are in terms of the number of evolutionary steps to produce them. Now, evolutionary steps here is not like the canonical definition of evolution that people usually have in their mind. It's actually more in terms of causation, the amount of causation necessary to build a particular object. So you can think, if you have most of us are not chemists, I'm not a chemist, but if you think about, you have your atoms and you can stick them together to make a bond, you can take that, any part of a molecule you make, and reuse it to start to build up to a final molecule that you might have detected. And the shortest path to do that is actually the one that we call the assembly index. That's a complexity score that molecular object gets. If chemistry is a little confusing, you can also think about Lego. If you had a bunch of Lego blocks on a table and you wanted to make a particular structure, like a castle or something, you could take blocks and stick them together and then reuse parts you've already made and try to look for a short path to produce that final object. And that's actually, by looking at the shortest path, we can measure the complexity in kind of a robust way. That's actually something that you can measure with standard spectroscopic techniques in the laboratory, like mass spec and infrared and NMR. And that's one of the reasons I'm incredibly excited about assembly, is that it actually is measurable and does seem to be an intrinsic property of molecules. And then what we do to actually implement this for life detection is we just look for things that have a high assembly index and high abundance, with the conjecture being that unless there's something that actually had the information necessary to construct that specific molecule, you're never going to find it in high abundance because of the combinatorial explosion of chemistry, because chemistry is so large that no planet could exhaust all of the possibilities of chemical space, even for small molecules. So if you find a complex molecule in high abundance, it's a sign that a system had to evolve and select for that specific structure to exist. And so because we can measure this with pretty standard spectroscopic techniques, we can actually use it in flight instrumentation to go and look on other planets for complexity, instead of going on and looking on other planets for DNA or RNA or any specific molecule that evolved on Earth.
Now, how does evolution play into this? In other words, what is the process of evolution and, changing? How does that relate here?
Yeah, this is a great question. So I think these it's hard when you're trying to build a new theory and you have to use existing words. So I'm always having trouble with trying to develop new concepts, but not really having the right words for them. So I use words like evolution, selection, information, complexity, causation, like all of these things kind of bundled together and meaning something about the same thing. And so evolution here doesn't necessarily mean strictly evolution in the sense that an evolutionary biologist might have come to understand it, which is, like Darwinian evolution, for example, is vertical descent with mutation and selection on variation. In assembly theory, evolution is actually a much more active process. We're really talking about selection within the space of possibilities. Like if you imagine all of chemistry, it's actually too big to imagine, but maybe you imagine the Lego universe and all possible Lego structures that you can imagine, also too big to actually physically build. Evolution and selection is the process of constructing new objects based on the things that you've already made in the past. And so in assembly theory, we envision a universe that's basically constructing itself, and evolution is the process of how things come to be selected to exist out of that process, because the space of possibilities of things that could exist is far too large for the universe to exhaust them all. And so selection is the mechanism by which some things are some things are basically constructed and other things aren't. And it becomes very path dependent and very historically contingent, because as you're building up into a more and more complex space, a more and more assembled space, the things that you can construct in the future are always built upon the things in the past. And so you have these very tight constraints that become the history embedded in the objects as far as what you can construct in the future. And that's kind of easy to think about even with like modern technologies. So, an example I like is to think about transistors, which are, in so many technologies today. So they've become this sort of historically contingent component that's used to make a lot of new technologies. And so it's excluded this, like a lot of other technologies from existing that don't use a transistor, just because transistors are now very efficient to make. We have lots of factories that produce them. They're present in lots of technologies. And so this kind of idea of this historical contingency reuse of parts and constructing into the world of the complex that way is really foundational to assembly theory and how we describe basically how the universe works, that the universe is actually, in some sense, path dependent when you get to chemistry, and that path dependence is actually a feature of the objects in terms of how they're assembled.
Does assembly theory make predictions? In other words, can we maybe perhaps contemplate the future of life? Will it get different than what we see around us right now?
Yeah, so the theory is really in the early stages of development, but one of the things that we are working on and I'm really incredibly excited about is the kinds of predictions that we can make with the theory. And so and also they should be, things that actually lead to new technologies or new experiments and new ways of thinking, right? That's the hallmark of a good theory. So I think some of the kinds of things that we anticipate being able to do are actually being able to take sort of the structure of the assembly space. If you think about this idea of building an object up stepwise and then having this sort of minimal path to construct the object. So you're thinking about like your Lego castle and you're looking at sort of the minimal set of components necessary to build it, where each of the components has nested in it the things that you built before. So that's sort of the visual. Those pieces that were in that assembly process actually can be used again to make other objects. So it kind of gives you now a constrained space of structures that you might expect to see in the future evolution of that system. And so if you're thinking about, technologies now, I actually am really thinking about applying this kind of idea to design of artificial intelligence algorithms and how we can actually make them more built into evolutionary principles. And I know other people are thinking about applying assembly in that space also. But the place that I'm really excited about it is actually predicting chemistry, and in particular, making the study of alien life a predictive science, which is pretty radical actually in the field of astrobiology. Because as we were talking about a little while ago, most people, when they're thinking about trying to look for life on other planets, are doing it by analogy to life on Earth. So we're thinking about, can we detect DNA on another world, or can we find amino acids, or how do we detect oxygen and methane in the atmosphere of an exoplanet? So it's very Earth-centric. And I think the opportunity that assembly affords is actually being able to predict what kinds of chemical systems might evolve in different geochemical contexts. So if you imagine you have a planet with a certain kind of mixture of molecules on the surface that are produced just because of the geochemistry in that planetary environment, I think we can actually predict the kinds of evolutionary histories that might emerge out of that. And so that to me is incredibly exciting because it makes alien chemistry geochemically dependent and also predictable. Just on the note of making predictions with assembly theory and things I'm really excited about. So one of them is trying to predict what kinds of life might emerge on other planets, which I think is within reach and is pretty radical as far as how we've been thinking about looking for life so far, because we haven't really thought about it as a predictive science where we actually really could predict what kinds of evolutionary systems might emerge on different planets. But the other thing that I think I'm most excited about is trying to actually be able to pin down the origin of life transition. And so when I was a postdoc working with Paul Davies here at ASU, I wrote this paper in 2013 called The Algorithmic Origins of Life, which was about the origin of life and whether it was possible to rigorously quantify that as a transition in informational and causal structure. And that's kind of like a lot of words, but basically the idea was somehow if there was a physics that described life and life was different than physics as we know it, it was because information is a causal category in life and not in non-living things. It turns out it's incredibly hard to formalize that idea and have it be at all consistent with standard physics, or to be something that you can actually objectively talk about as a measurable property of systems. So like information theory, for example, is notoriously subject dependent because it requires a labeling scheme. And so it wasn't really until very recently, after I started working on assembly theory and really thinking about assembly and how assembly captures the amount of causation in molecules and also potentially in other objects as we're validating the theory in more spaces, and kind of captures the idea that a lot of constraints and information went into the construction of this object. That's really what the theory is about. That I really started to get excited that we might be able to formalize the origin life transition using assembly theory. And the reason I think this is incredibly promising and possible is because of these, well, there's a few reasons, but one of them is these sets of experiments that Lee Cronin's lab was doing. So Lee is the originator of assembly theory. He really came up with the idea of assembly index as a measurable property of molecules to measure the amount of evolution in a molecule. And I started working with Lee on the theory early on because I was so excited about this idea. But his lab was pretty clever. They came up with a way of measuring assembly index with mass spectrometry, and then they took a whole bunch of samples from living and non-living systems, and they were able to show that there's a boundary above which you don't find any molecules that are produced in non-living samples in terms of the assembly index measured for those molecules. And it has to be assembly index plus copy number. So it's actually big A assembly, which is a quantity that we define in one of our papers, which captures this amount of causation and selection. But what they did in that paper was really focus on the assembly index measurement because they already had abundant molecules in all of their measurements. And really what they saw is this very abrupt threshold. So if you imagine chemical space as like you're building up chemical space by adding an atom at a time to a molecule, and basically, or a piece at a time to a molecule, like thinking about expanding your space of Lego structures as you're expanding your space of chemical objects. And it grows so exponentially fast that just a few steps into that space, you actually have so many possible molecules, a planet can't exhaust them all. And so what we see when we actually are looking at chemical space and thinking about assembly is that there's an abrupt threshold where above a certain assembly index, we conjecture that there shouldn't be any objects formed that aren't part of a living system. And that's exactly what they saw in this set of experiments. So what gets me excited about that is we see an abrupt transition point in assembly where we understand abiotic things can produce things below this assembly and only living things can produce it above. And that's actually what motivated assembly theory as a really promising framework for life detection. It was really the first kind of agnostic approach to life detection that was experimentally verified, and still the only one that has like a robust theoretical framework underlying it and a measurable property of molecules. And so that part got me really excited that this might be a real physical property. And then if this transition point is a real feature of physical reality, as we're starting to see it looks like in the way that molecules are structured, it should allow us windows into the origin life transition itself. And so from the other side of it, so that's the empirical sort of that there's this idea of a phase transition from biotic to biological systems associated with the assembly of the system. Like below a certain assembly, you don't see it's only abiotic and biology can exist there, but above that assembly, only biology or only living things can persist because those objects are so complex that they require evolutionary scaffold of complex objects in order to make these other complex objects. And so all of them have to kind of coexist and co-constrain in an evolving architecture in order for you to even observe things of that complexity. So what I got really excited about is that what we see from the theoretical side is evidence of a transition point in assembly theory, in this idea of the assembly space, these recursive joining operations where you're reusing parts to make objects. If you look at the structure of those spaces, they seem to all have a selection mediated phase transition at a certain threshold value, which depends on the structure of the space. So it might be different for molecules than it would be for languages, for example. But they all have a phase transition. It's a general property that would be associated with the boundary that is the origin of life. And so we're working right now on formalizing that. I'm incredibly excited about it because I have waited my entire career basically to try to figure out what would be a way of formalizing the origin life transition. And I think we're on the cusp of that. But if, that works out, then you would be able to predict what the transition point is and the complexity of a system when you would observe an origin life event. And you would also be able to say something about the structure and relationship of objects in order to actually have them mediate an origin of life. And if we can do that, I think we're off to the races, because then we understand what the experimental problem is and what we actually need to look for in the lab. And I think we're pretty close, but we'll see. I mean, it's really tough. I thought we had it worked out totally a couple times already, and it's kind of, it's a little elusive, but we're almost there.
Now, the immediate question that pops in my head is, will this speak to commonality? In other words, all right, you understand that, this happens and how it happens. So the question is does it tell you, does your research tell you how common life could be in the universe? In other words, does it sit there and say, like with the research into abiogenesis, does it say this could be really, really rare or really, really common? Is there any insight there within this?
Yeah, that's actually one of my key objectives. So I was trained in cosmology formally, and so in some sense, I have a very cosmological perspective on the nature of life in the universe. So a lot of the ways that I frame the problem are heavily biased by my training. I try to be aware of that, but it's really hard to get outside of the dogmas and the things that you were trained in and the way that you sort of naturally think. But in cosmology, there's a strong correspondence between the way we talk about things in the universe out there and the way we do experiments on Earth. So there's a deep relationship between our understanding of Big Bang cosmology and particle physics experiments. And I always thought that the origin of life was an important missing parameter in cosmology. So if you look at a pie diagram for the universe, there's, it's like the standard, 75% dark energy, 24% or 20% dark matter, 4% baryonic matter. I don't remember exactly the percentages in the pie chart. It's been a while since I looked at one, but there's no percent of animated matter, right? We just don't know how much material in the universe is alive. And I really want to know that. And so I was always very unsatisfied with this sort of current paradigm of searching for life, based on luck. It's really, a lot of it is based on the idea that we're going to get lucky and we're just going to recognize it. And if we're doing the science properly, we should not just be thinking about getting a lucky moment, but actually constraining that probability. So we don't want to just say, oh, life is common. We're likely to see it if we just look at 10 exoplanets, or if we go to Enceladus with a slightly better instrument, we'll be able to detect life. We actually don't know that. We don't know how common life is. And so what I wanted to be able to do was to do surveys of different planetary environments to actually constrain the probability that life could emerge. And so when I started getting into exoplanet science, which is one of the fields that my lab is involved in, and we've worked quite a bit on life detection in exoplanet atmospheres. But one of the reasons I got into exoplanets in the first place was because I wanted to constrain this probability for the origin of life. So a lot of people want to do exoplanets because they want to discover aliens, but I actually really just want to know what life is, and I want to know how likely it is in the universe and how we understand that mechanism. And so I was thinking about it from the other perspective. So at the time, I was thinking we should do these kind of surveys of exoplanets, and we don't need to get a ton of data, but we need to get data that actually allows us to rule out which planets are dead and which ones might still potentially host life. But what I've learned from that field is the measurements are incredibly hard. The technology is really pushing the boundaries of what we can understand with such limited data. So they're doing an incredible job in that field, trying to build better algorithms for extracting data from these telescopes, building better mirrors, all this stuff. But still, it's going to be really hard to get any kind of confident measurements of any planets, let alone hundreds of them or thousands of them. So I have kind of pivoted from that being the right way of constraining that probability to really thinking about original life experiments at scale. And a lot of that is inspired again by Lee Cronin, because he's been basically trying to build this technology in his lab for more than 10 years, probably 15 years or longer. But when he started getting interested in the origin of life, he was thinking about how can he get robots to do this synthesis, and the idea being that if we could build a technology that could do chemistry robotically, do digital chemistry as it's called, it might allow us to have a platform where you could do a lot of chemistry experiments all at once. And therefore, it could increase your likelihood of finding interesting chemistry that might be relevant to life. And so one way to think about it is actually building a search algorithm for chemistry, with the problem being the technology is limited because chemical synthesis is hard. And the way that most chemists do chemistry in the lab is like a one-pot synthesis, and you need the chemist in the lab to do all of the manual labor of moving things between different vessels. And so Lee invented this technology of this robot that can do, like the robot is completely enclosed. It has all these like moving levers and stuff. It's kind of crazy to watch the videos. There's some of them on YouTube if people are interested, but it has a universal programming language associated with it. And it can read in the literature, and it can actually do any known chemical synthesis, with a few caveats because of, different kinds of chemistry is just really hard to do. You're dealing with physical materials, but in principle, it's universal. The ontology is universal. So it's basically a universal programming language for chemistry. The reason that this is exciting for constraining the probability of the origin of life goes back to this connection between cosmology and particle physics I was mentioning, because, I grew up, academically speaking, in love with particle physics experiments. And one of my favorite experiments is Super Kamiokande, which is looking for proton decay. And what really fascinated me about that experiment is that no one has actually observed a proton decay in the history of the entire universe. But some of our theories of physics predict that it could happen. And therefore, we built a really massive experiment in Japan, basically to try to detect a proton decay, or if we don't detect it for a certain amount of time, we bound the lifetime of the proton. So basically, this experiment's been running for a number of years. I don't know how many now, but as long as it runs, the longer that we don't observe a proton decay, the more and more constrained we're making the lifetime of the proton. Sorry, I said the mass, the lifetime of the proton. So we know that we have certain bounds on its lifetime, and it keeps getting longer and longer because we still haven't observed an event. And the reason I found that inspiring in the context of Lee's experiments, and also thinking about this exoplanet problem, is we don't know the likelihood of life in the universe. We don't know how to probe that question. But if we could build a massive enough experiment of these computers, as Lee calls them, these digital chemical synthesis engines exploring chemical space as like a chemical search engine for alien life, and we actually know what we're looking for. We have a theory to guide the search, which I'm hoping assembly theory is the right framework, because we've been investing so much and so many ideas into that space to try to build it into this problem, that we would be able to constrain the probability of the origin of life. So if you do the origin of life experiment properly, even not observing the origin of life gives you information because it tells you how rare it is. And I think this is something that we really haven't thought about with this problem, because we think life is so obvious, it's so likely, it's such a universal thing in the universe. But the truth is we don't know the answer to that question. And so I think we really need to think about the experimental paradigm for the origin of life as one where we're looking for alien chemistry emerging de novo from an unconstrained chemical system. And the longer that we don't observe that happening, the more we know that life is rare in the chemical space of all possible chemistries that a planetary environment could generate. So in the book, I call this a planet simulator. I don't know exactly what that experimental program is going to look like. Lee's lab is developing a lot of the technology, and Lee and I are working together to basically try to build into an origin of life initiative that might be able to raise enough money to do the experiments properly. But it's a lot of work, and it's a lot of science to be done. So it's really exciting, but that's where I stand on the probability of the origin of life. We don't know. And I think it's an experimentally tractable problem with the right theory and the right minds in the room and the right experimental equipment. And I would like to know.
Okay, now evolution, again on this theme.
Yeah.
On evolution. So here we are, humans, and we evolved, and it took forever. You know, we're here after 3.8 billion years. And now we are building machines and flirting with artificial intelligence. Do you think that artificial intelligence represents a natural next step of life in the universe?
I do on our planet. So I think if you take, again, I want to preface that I'm approaching the problem of life from the perspective of theoretical physics. And theoretical physics as a discipline, or actually not even as a discipline, I guess like there's the theoretical physics that's studied in physics departments, and then there's theoretical physics as something that humans have done historically as a way of trying to develop new abstractions that are very deep and represent very broad regularities about the world that we observe. And I feel like what I'm trying to do is the latter, like really coming up with the deepest possible explanations that explain a broad swath of phenomena. And so when you're approaching the problem of life from that perspective, which is very different than the biologist perspective of the problem, right? So biologists tend to study biology as it evolved on Earth and study organic forms. So they have kind of a conception of life that might be quite different than what I'm saying, although I think some things resonate. But when you're approaching it from this perspective, you're really trying to encompass alien life and origins of life. You know, the view that I've ended up on is this idea that life is something about how the universe generates complexity, and it really requires constraints in information and causal structure to be able to enable that. And assembly theory becomes a natural language for talking about it. But basically, what that implies is that any object that's produced by evolution is a manifestation of the physics of life. And evolution is very broad here, right? Evolution is selection and the mechanism of generating new structures based on things that have existed in the past. And so technology is just as much life as biology is. And there's a continuity there because obviously things like large language models that are trained on human languages would not exist without humans first existing and humans forming social groups and evolving languages and also evolving technology to store enough language in computers for these algorithms to be trained on, right? So it took thousands of years of human evolution in terms of technological evolution before we could even get to something like an LLM. And it obviously took billions of years of evolution on the planet to go from geochemistry to something like us. So it seems to me that, yes, it is a natural continuation of the process of evolution that's been happening on this planet for billions of years. And I think that might seem uncomfortable to some people because they might not want to qualify technology as life. And there I make a little bit of a caveat because I think when I'm talking about when life is all the things that require evolution in order for them to exist, require selection and a process of information refinement, that's sort of the space. Like if you want to think about like how in theories of gravity, you need a space-time background in order for gravitational forces to act. But obviously like mass is the thing that kind of mediates it. I kind of think about life and alive that way. So life is the space of all of the objects that are, they can't happen for free. They require historical contingency and evolution and selection to exist. I don't believe in spontaneous fluctuation of complex objects. I just think it's impossible. I think that the only mechanism for them coming into existence is evolution. And I think that's consistent with the observational data and actually, what we know about the original life. So I say believe because I'm willing to change my beliefs at any moment with empirical evidence, but I have a strong conviction about that right now as a theorist because it seems most consistent with the observational evidence. That's very different than what standard physics says, which is that any object can spontaneously fluctuate into existence with a very small but nonetheless finite probability. So there's a sort of major dichotomy there between what I think now and what I was taught to think as a physics student. But this point about life is all of these things that don't happen for free and they require evolution to construct them. But there are some objects that exist, things like human beings or a cell, which are much more constructive. They're much more creative. They're much more active in the process of generating themselves and also other structures. And so like there's kind of a sliding scale between non-life and life, but also life and alive, that they're not binary categorizations. But you can, I wrote this essay with my friend Michael Lockman years ago about how life and alive are not the same thing. And so you could be life, but not alive. And so I think the example we gave was a little bit of a play on Schrodinger's cat, which is like alive and dead at the same time because of quantum superposition. And we were saying, well, a dead cat is life, but it's not alive, because dead cats don't come into the universe apart from an evolutionary process. But nonetheless, you obviously can recognize that it's not alive. And assembly theory right now is really good at recognizing life. I think we have some work to do to convince people that we're also capturing features of what it is to be alive, but that's part of the theory of the phase transition, the origin of life, and some of the things that we're doing. We're trying to understand agency right now in assembly theory. So that's kind of the frontier of the theory right now. But I think the distinction between sort of active and like what the space-time is and what processes are dynamically operating is important.
All right, we are out of time, Sara. Thanks for joining us today. And everybody should check out Sara's upcoming new book, which comes out just a few days. Life as No One Knows It, The Physics of Life's Emergence by Sara Imari Walker. And that'll be out in just a few days.
Thanks so much. I really appreciate it.
Event Horizon and my channel are now available as a podcast on Apple Podcasts, Spotify, and YouTube memberships. Early ad-free episodes, bonus episodes, and sleep-focused content. Sign up now by clicking the links below to your platform of choice.